Okay, if the object remains stationary, that means the net force is 0. Okay, so you should just look at this free body diagram right here in the red box and realize that the normal force, which is that plus the tension in the string, is going to equal the weight. And you should be able to see, therefore, that the normal force is going to be less than the weight. Remember in class I said if someone's standing on a scale, the scale reading is a normal force. If someone's standing on the scale and is pulling up on your shirt, pulling you upwards a little bit without taking you off the scale, well, the scale reading is going to be less than your weight. This is the equation for that. Look at number 2. Okay, so here she is. Here she is right here. She has a weight, and then she has her arms, parallel to each other and perpendicular to the bar. So here's the weight. You can assume that each of these tensions, because she's right, it's like the chains in a swing. If you're sitting on a swing, the 2 chains each supply what? Half the weight. Okay, so this is an equilibrium. The net force is 0, I meant to say. So 2t has to equal W, and you can solve it from there. So it'd be like the free body diagram would be like this. And those 2 t's have to be the same. Okay, let's look at number 3. This is just like the one we did in class. Was tension in one of the strings. Okay, so the weight is mg, which would be 9 times 10. And then we got tensions in each of these. But because the angles are the same for both, we can say T1 equals T2. So let's just solve for, let's say, T1. So I'm going to just isolate T1. There's XY axis. The weight's along there. Okay, so if I were to draw a free body diagram, or just the slanted force there, T1, here's XY axis. We got the weight going down. We got T2, but let's not draw T2. So let's draw the X and Y pieces, components of T1. So that's T1Y and T2Y. Now, I really don't want this angle right here, but that's given as 35. Now, the angle from Y doesn't fit my Q equations, QX and QY equations on the equation sheet, so let's use this angle, which is from the x-axis. So 90 minus 35 is 55 degrees. That's the angle I want because it fits my equation. So T1y equals T1 times sine of 55. I'm using equations on the equation sheet. Qy equals Q times sine of theta. The theta is always taken from the x-axis if you want to use those equations. Okay? So that really doesn't look like it gets me anywhere because T1 and T1y are unknown. But really, T1y is not unknown. Look, let's go back to this picture. There's T1y. There's T1x. Now, you should realize that T2 has T2y equal to T1y because the angles are the same. And T2x equal to T1x because the angles are the same. So you should see now that T1y really is half the weight because T1y and T2y both add up to be equal to weight, and T1y has to equal T2y if the angles are the same. So now you have that. You can plug that into here, and you can solve for, you can plug that into here. Then solve for T1. Okay? You can do that. Oh, remember that M, so the weight is 90, not 9. 9 times 10. Okay, right here. So we got, let's draw a free body diagram. Okay, so there's that force. Pulls it with a tension of 100 newtons in the string, in the cord. Then 30 degrees above horizon, so that's from the x-axis, so that's good. Okay, so the total mass with the girl on it is 60 kilograms, but I want the weight. So that'd be what? 60 times 10, you can do that. So we have that. What is normal force? Normal force is pointing up. Now, they don't say anything about friction, so I'm assuming there isn't any. But it doesn't really, that doesn't even matter, because all we're doing is finding the vertical forces. So we're focusing in on these only. But don't forget that T1 has two parts. T1y, two components. T1x and T1y. And don't think that the normal force is the y component of the tension. I'm sorry, there's no ones on there. So you guys just see that there's no net force in the vertical direction because the sled's not accelerating up or down. So the sum of the forces that point up which would be N and Ty, equals this sum of forces that point down, which would be the weight. So you can plug the values into there. You gotta find Ty using the equation T equals Ty equals T times sine of the angle, which would be 30. And T is 100, given up here. Weight is equal to mg, I already told you that. So you can solve for n easily, the normal force. Now it's the same problem, but now there's friction. Okay, so if you're moving with constant velocity, that force, which would be, look at my former picture, Tx, not tension, would equal the friction if you're going at constant speed. Because acceleration would be 0 if you're going constant speed, net force would be 0, and so the forces are balanced. So if you find Tx, which would be T cosine of theta, you got what the friction is. What is the tension is given right there, as it was before. Okay, this one. Now, the guy's pushing a kid on the sled. So, let's draw this picture. Okay, so, so we got a downward force of 75 newtons on the sled. The sled has a weight, well, a mass of 50 kilograms, so there's also, let's call that the applied force right there. There's a weight, and so that equals mg, m being 50 up here. Okay, that force is 75 newtons. That applied force is 75 newtons. Angle 40 to horizontal. Okay, 40 degrees. Find the normal force on the sled. Okay? You should realize that, first of all, you gotta find the x and y components of this guy right here. Here's the x, ax, applied force x, and there's ay. Now in this case, you should realize that the normal force, now look just at the vertical forces, so n, the sum of the forces that point up equals the sum of the forces that point down. Because it's not, the sled and kid aren't accelerating up off the ground or down into the snow. So that's all you do. Ay, you should be able to do these by now. That equals a times sine of 40. Weight equals mg. So you got made. Okay, let's go to number 7. What is the tension of the rope between that D and wall A? Okay, so they're looking for this tension right there. Okay, we did this in class. A similar one. And some of this will be on a test too. So, first of all, here's your free body diagram right here. This is the weight of the 25 kilogram mass. So 25 times 10. Then we have this force right here. I don't need to find that. Let's call that T. I don't know. Let's call that TB. Let's call this TA. this would be TC. Okay, what's the tension role? Okay, so I'm looking for tension A. Okay, well, first break that up in X and Y pieces. Okay, here's the Y. 3-finger rule. Okay, so here's T-A-Y. And then here's tension A, X component. So there's the Y component of what I'm looking for. Here's the X component of what I'm looking for. Okay, so I do know that this arrow is going to be balanced out by the weight, which is TC. So I can say T, the Y component of TA, has to equal the weight, which is TC. And the weight's mg. Okay, so I have that one now. I know that TAX is equal to, interesting. Okay, well, disregard this right here because I don't need it. Okay, so TAY equals Y. TA, Y component of TA, right there, is equal to the weight, right there, because this knot is at rest. Okay, so let's draw our triangle. This thing right here. Okay, so I'm drawing this triangle right here. So this is TA, that's what I'm looking for. And I have TAY already. You're gonna find it for me. So this is T. Oops. All right, hold on. Okay, so we got TAY equaling the weight. Got this 45. And so I'm looking for what TA is. So use trig. I would use QY equals Q times sine of theta. So this would be TAY equals TA sine of theta. And I can solve for the tension by simply using algebra, rearranging this. Okay, and that would give me TA. If I were asking you for TB, this guy right here, all you do is find TAX the same way, because TAX would equal TAX right here would equal TB. Okay? What's the net force acting on this block? Okay, so let's draw it's not necessarily at, 0. They don't necessarily balance out. So let's check out what's going on here. So let's draw XY. Okay, so we got 30 newtons at 30 degrees. We got 15 newtons pointing down, and you got 40 newtons over there. Okay, so what I would do is, maybe XY table would help for this, but what I would do is on the slanted force, find what these are. So that'd be, this is F2, so this is F2Y, and this is F2X. So find those using trig, okay? And then this 15 is F1, and this 40 is F3. Well, after you find those, you find the net force horizontally. See if you find F2x by doing F2 times cosine of theta, which is 30. And then whichever one's bigger, F3 or F2x, you subtract the smaller one from the bigger one. And that gives you, I don't know which way it's going to go, left or right. That will give you the net force in the x direction. Okay, so I don't know if F3 was bigger. Oh, I know F3 is going to be bigger, just looking at it, because 40 compared to something less than 30. So that's going to be 40. Now let's do it this way. This will be 40, or F3 minus F2x. Then I'm going to solve for the same thing for Fy. And, F2y is going to have to equal F1. Well, how do I know that? F2y is equal to 30 F2 times sine of 30, which is half. So 30 times sine of 30 is 15. Why can't I write this? I'm off the screen. Hold on. So 30 sine of 30 is F2y. And so that's 15. And you can see that this is 15. So Fy, the net force in the y direction, is going to be 0, because these two guys are going to cancel each other out. So what is the net force? It's just whatever this is. Now, if Fy didn't cancel out, I'd have to use Pythagorean theorem with those two. The sum of the net force would have to equal the square root of EFX squared plus the square root, I'm sorry, it would have to equal, the total net force would have to equal the sum of the squares of the x net force and the y net force. But I'm not going to do that, okay? Because one of them turned out to be 0. So it simply equals what you solved for it right here. What you solved for it right here. Okay. This one. Oh, we're going to inclined plane things now. Okay, so so I'm looking for the normal force. That's so remember, the way you do this is you got x and the y like that, This is the same as the angle here, which is 30. Remember I said in class, the angle between the weight and the y-axis is slanted force, and the y-axis is always the same as the ramp angle. Okay, let's straighten this out. So what I do is tilt it, like I tilt it a little bit so that the cross is straight instead of crooked. So again, you got to do your XY axis so that the y-axis is going through the normal force, and the x-axis is going along the ramp surface. So that's the normal force. We got friction this way. We got weight like this at 30 degrees. Okay, where is this? Okay, I'm just looking for the normal force. And if we look at this, normal force is simply going to equal the y component because there's no other force. I'm sorry. Yeah, the net force horizontally is 0, so the forces have to balance. Normal force has to balance out with Wy. And there's also Wx. But I don't really concern myself with that because it's horizontal, not vertical. So N, normal force, equals not the weight, but the y component of the weight, which would be W. Now be careful. This is W. Wy is Q. Qy is Q times sine of theta. But when I do that, I use the angle from the x-axis, the angle from the x-axis, which would be 60 degrees. Using my Qy equation, you have to do the angles from the y-axis. So that's sine of 60. So weight is mg, of course. So 8 times 10 times sine of 60 equals the normal force. Okay. Now this block is sliding down. No, it's not. Okay, sliding down 30. Is this the same question as this? Yeah, everything's the same. So I can use the info that I had in the previous question. Okay, it says it right here. Do that problem first. We just did. Okay, the coefficient of static friction, that means if it's at rest, is 2. And the coefficient of kinetic friction is what I'm looking for. Wow. No. The coefficient. The coefficient of static friction. The coefficient is 0.2, and the coefficient of kinetic friction is 0.13. So what is the kinetic friction acting on the block? Okay, so I already have some things. I have my diagram over here. Let me just, I can't cut and paste it, can I? I don't know. Oh yeah, I can. Here we go. Try it. So I'm going to copy this. Wow, that didn't work. What's that? Okay, I better not do that. I don't know what's happening. Okay, so I have my diagram right there. I know the normal force. I can solve for Wx and Wy. Okay, so come on. Can I move this? Okay, so I'm not going to redraw all that. So I'm just looking at over here. Okay, so here's W, X, And there's a friction. Let's connect. Okay, so let me see. I have to figure out if this block is at rest or if it's sliding. So to do that, I gotta find out what the friction is, both of them. So, friction. Wow, what's going on here? Friction, too thick. Friction is the coefficient of friction times n. So static friction maximum is 0.20 times the n from over here, whatever your answer is. Okay, so we have that. So I'm not gonna, I'll let you plug that in. Okay, then I'm gonna do the same thing with kinetic friction. That's mu k times n, which I have. So that'd be 0.13 times n. So actually, I didn't have to find Fs max because all they're asking me for is what's the kinetic friction. So it's very simple. I just had to use that equation. You're solving for this right here, the kinetic friction. Wow. Okay. This is the next one. It's the same problem. It's the same problem, but what's the acceleration block down the ramp? Okay, so we have the kinetic friction already. We have Wx, or if we don't have it, you can find it easily over here, because Wx is equal to the weight times the cosine of 60, the angle from the x-axis. So we have Wx. So your net force horizontally would be Fk, which you already found. Oops, the bigger one minus the smaller one. So I'm assuming if it's sliding down the ramp, Wx is greater than Fk. So it'll be Wx minus Fk. The kinetic friction. The x component of the weight minus the kinetic friction. And you can solve for that. Okay, now a string's pulling up on this. Okay, so we got the weight going down. We got the normal force going perpendicularly from the surface up. It's normal force. We got the x component of the weight and the y component of the weight. I'm kind of being lazy here by not drawing it straightened out. Maybe you want me to. So let's straighten it out. Okay, here's the weight right here at 20 degrees. Remember, the angle always goes between the weight and the y-axis. So really, I'm concerned about the 70 degrees here when I find out what the Wx and Wy are. So here's Wy, here's Wx, here's the normal force pointing up, and here's Wow, here's 2,000 newtons, 2 kilonewtons is 2,000 newtons of tension pointing to the left. Oh, there's no friction to worry about. Okay, so what am I solving for? The mass. Okay, so, well, if it's resting, find the mass of the inflation free, which is resting. Okay, so the string's pulling it and keeping it from sliding down. So the string's force, the tension, has to equal dWx. So we're trying to solve for the mass, which is, you'll get it from finding the weight of the box. Now we find the weight of the box. Let's draw this guy right here. This triangle right here. Because it's from the x-axis. So this is 70. Oops, give me a pen. This is 70 degrees. This is Wx. That equals T, the tension, because it's in equilibrium. Horizontal forces balance each other out, cancel each other out. So I have that. I have that value. What am I looking for? The hypotenuse. So you use Qx equals Q times cosine of theta. So Wx equals Q times cosine of theta. And be sure you pick the angle from the x-axis, not from the y-axis. So you got T. Tension's given right there. You don't know weight, but you know cosine is 70. Okay, so once you find weight, do an mg equation on it, and so solve for the m. Okay, these aren't too bad. That was a good quiz. Okay, I hope you guys learned from that.